Welcome, everybody. Hi, Dr. Skogestad. Okay, let's start with this session. So, welcome, everybody. For me, it's a great pleasure to introduce you in this first plenary talk to Professor Sigurd Skogestad. I'm sure that many of you already know him, at least particularly in the field of process control. I would like to say that Sigurd Skogestad in this field in process control is a very famous. Is very famous. He's very famous. So I think that talk about his works are his extent. So I think that to do that I can take a lot of time, no? But at least but not at least in the field of process control is a very famous person, and in the field of control, I think that many of you know him. So before to give the word to Professor Skogestad, I would like that Dr. Jesus say something about certain picture that I think it could be nice to present before the presentation of Professor Sigurd Skogestad.
No, Hector, I will do it at the end.
Okay. So I will give the talk to Professor Skogestad. So Professor Skogestad, can you begin with your presentation, please?
Yes, thank you very much, Hector. Thank you for inviting me to give this presentation. So it will be on advanced process control. So that's a topic that's interested me for many years, since I took my PhD with Manfred Murari back in the 1980s. So advanced process control can be many things. We have the classical advanced control, which goes back to the 1940s with the PID controllers, cascade and selectors and so on. And then we have the more newer MPC, which is also actually about 40 years old. So it's also been around for a long time. And both of these are used in the industry. I remember when I started my PhD, we thought that these old methods would go away, but they're still here. So maybe it's time to go back and look a bit more at these classical methods. And that will be the topic of this talk today. Just a bit of where I am. I'm located sitting in Norway. In Trondheim. So that's in the middle of Norway. It's close to the Arctic Circle. So the Arctic Circle is where you have, in the summer, north of the circle, you have 24 hours of daylight, and in the winter you have 24 hours of night. So we are just close to this. So you're welcome to come and visit if you are in Norway. Just a bit about myself. I mentioned I got my PhD in the US with Manfred Murari, early 80s or mid 80s. Before that, I worked a bit in industry. But since then, I've been in academia here in Trondheim at the university, NTNU. You can find more information about me on my homepage if you check it out. It's this old-fashioned homepage from the 1990s. So my interest in terms of research is really to find things or develop tools that can help engineers do their job better. So that's always been my interest. So I want to make something that's rigorous, but also useful. So one example is this PID tuning rules that I published back in 2003, which I called probably the best simple PID tuning rules in the world. Actually, I tried to give the paper this title, but it was not accepted by the journal. But anyway, this is like a subtitle. So that's one example, I think, of something I liked working on. But today I will talk about more into optimization and how that links to control. So I will start by talking a bit about how we do control hierarchies. And then I will talk more into detail about classical advanced process control using selectors, input transformations, split range control, and things like this. At the end, I will discuss a bit MPC versus classical advanced process control. So this slide is just to give you some of the notation. So when I talk about control, then we're talking about the problem where you have a given set point. So in optimization, you just have a cost function to minimize, which could be economic. But in control, the cost function is related to keeping the control variable, CV, the output Y, close to a given set point or reference. And for this, you use the inputs, the manipulated variables. But if you look at it, how a real system is controlled, it's not in a simple fashion like this. This shows a typical control hierarchy in a chemical plant. Here you can see 5 different layers, and each layer is also subdivided into different boxes representing different parts of the system. And the main basis for this division is timescale separation. So at the bottom you have the stabilizing layer. Above that you have the advanced control layer on a minute basis, and then you have economics typically on an hourly basis. And this is usually steady state in chemical plants. So this shows you how the real system looks with the different decision layers. Now, if you look at how people in academia are working, they're trying to replace all of these layers at the bottom, the 2 control layers in optimization, by what is now popular to call economic MPC. The E stands for economic. Now, in this talk, I will be talking about MPC, but that's going to be the normal MPC just on set points. But this economic MPC is of course, going to be the optimal way of doing things. The problem is that it's very difficult to make it work in practice on a big problem because it needs models and tuning and so on. You can try to keep some of the control layer in the bottom and replace just the economic layer and the supervisor layer by this. But also this is difficult to do in practice, at least for a large problem. So for large real systems, we are back to this hierarchy that I showed. And so the focus on this talk will be on using this hierarchy, and especially on this upper control layer. So that's going to be the focus in talk, and talking a little about how it links to the optimization. So how do we design the control system for such a large process? Well, it's basically, there's many ways of doing it, but the way I recommend is first to consider the economics. So you look at the optimal way of operating the system, usually just from a steady state, by minimizing a cost subject to constraints. And then you want to translate it into control. So you want to find good control variables to keep at constant set points. So the first thing that you should always control is the active constraints. And for the remaining degrees of freedom, you want to control something related to the cost gradient, which is something I also call self-optimizing variables. Now, when you have selected these, then you need to design a control system to do this. That will then usually consist of 2 layers. One is this supervisory control, or this advanced control layer, and then below there's this stabilizing layer. So in this talk, I'm focusing on this advanced control layer. So what are the objectives of this upper control layer? There's 3 main objectives. The first is, of course, to control this primary variables, CV1, the economic variables, at constant set points. And it's important, especially, to have tight control of the constraints to avoid backoff and economic loss. The second thing is then to do switching, because it happens quite frequently that these control variables change because of disturbances, and then you need to do switching of the control system. And also important thing is to keep an eye on the control layer below, the stabilizing layer. You must avoid saturation in that layer, because that can make serious problems. And this might also then require switching. So you can see there's a lot of switching going on here that we need to look into. There's 2 alternatives here, as I mentioned, main today. That's the classical advanced control, based on PID controllers and simple things. And then there's the model predictive control. So academia, the focus is on model predictive control. It's a general approach, but of course we need a dynamic model for the whole system. Another thing is that MPC is usually implemented only after there has been operation for some time, so we need to have something in the meantime. Not all problems are easily formulated using MPC. And also you should note that also with MPC, you need additional logic to do changes in active constraints. So if you look at how industry implements MPC, they have a two-layer approach where they first do a feasibility analysis, and then they decide on what to control based on the constraint priority list. And then after that, they solve the MPC problem. Anyway, what I would like to discuss today is some alternatives to this to find simpler solutions. So can we find solutions that require less information about the model? So one topic these days, of course, is machine learning. So machine learning in theory could be used, but it requires a lot of data. And also this can usually only be implemented after a process has been in operation. But then we have all these classical advanced control methods that require much less modeling, and they're still extensively used by industry. So I think it's a time to look more into these methods again in detail. The problem for the use and for the engineers is that there's a lack of design methods. Although it has been around since the 1940s, there's still not much methods you find in textbooks on how to do this. There's also some fundamental limitation, which is mainly that it's based on using single loop pairings, and this might not always work. Okay, so what is this classical advanced control I talked about, using simple control elements? Well, here I list 7 of these control elements that you can be using. Cascade control, feedforward, decoupling, adaptive gain, split range control, valve position control, selectors. And we know fairly well when these should be used. So cascade control, of course, you use if you have some extra measurement, maybe without a delay. Feedforward control, decoupling, we know that these 3 of these can be is often combined into what is often called function blocks in industry. They're just often static things. And I will be talking a bit about this today and looking into the unifying approach of what I call transformed inputs, which turns out to be related to feedback linearization. Then there's split range control, which you use when you have extra inputs. Valve position control also if you have extra inputs, but dynamically. And selectors. So selector is going to be one of the main, or really the main topic today. And selectors are used when you have changes in active constraints or when you need to switch between different controlled variables, different outputs. So when you have one input, for example, and many outputs. So how do we design these classical APC elements? Well, it's not easy. There's an industrial literature going back to Shinsky, has a lot of nice ideas, but it's not really systematic, and it's difficult to understand the reasoning in many cases. And if you look for academia, there's actually very little work. There's some mention about these methods in textbooks, but that's almost all you can find. There's very little systematic work there. So this has been one of my interests has been then to try to improve on this situation. So looking into then this last issue of selectors. So that's going to be an important part here. I wanted to show you a bit that this thing about selectors is not just something that engineers is doing because they couldn't find anything else. I want to show you that selectors have some basis in the original optimization problem that you're trying to solve. So this is an optimization problem that you typically want to solve at steady state. This is the steady state problem here. Minimize the cost subject to constraints. And very typically you find that the optimal solution is that all the degrees of freedom, or at least many of them, are used to satisfy active constraints. And if you look at it then in terms of the cost, what you will find that if you want to minimize the cost, it's important to control these active constraints tightly. And this is to minimize what we call the backoff because if you have a distance to the constraint, it generally gives you an economic loss. So I'll give you an example here of active constraint control. You just want to drive a car from A to B in the shortest time. So the cost function here is the time you want to minimize. The input is the power. the gas pedal. So there's some constraint. One is the speed limit, another is some safety limit to keep the car on the road, and so on. But if you have the case of a straight road, then we know that most likely the active constraint will going to be the speed limit. So if you can just have a feedback control that keeps you at the speed limit and do that tightly, you will be optimal. So you don't actually need any optimization for this. So the question is how can we identify and control active constraints in an efficient manner? If we can do this, we can probably optimize the operation without actually having an optimization problem being solved. So to understand a bit about this, you can look at constraint optimization. And if you know something about constraint optimization, you know that you can write this to solve this. You can introduce what we call Lagrange multipliers, or the dual variables shadow prices. And one way of decomposing the problem is illustrated here. This is called sometimes the dual decomposition. So in this case, you kind of guess the shadow prices, you guess the Lagrange multipliers, and then you solve an uncontained optimization problem, and then you iterate. Now the iteration can actually be done by controllers. So here I'm using just the PI controllers to control the constraints, and each controller adjusts then the Lagrange multiplier. And that those Lagrange multipliers go into these problems, where you can also solve by PI controllers and computing what the real inputs to the process. So this can actually be found to be optimal. So note here that there is a selector here, because this thing is because the Lagrange multipliers have to be greater or equal to 0. So when they're 0, the constraint is actually not active, and when they're non-zero, the constraint is active. So there is a selector here. But one problem with this way of doing it, this is actually a general way of doing it. It could be used for almost any problem. And this is actually a PI solution to a optimization problem. But you note that the constraint control using the dual variables is on a slow timescale, because you need a timescale separation here. So this will not be able to do tight control over the constraints. So you can look for another solution, which is this one, is where I directly control the active constraints using the inputs. But since there could be many active constraints associated with a given input, I need to use a selector here. So the selector is used to select the constraint that is active. So of course you have in this case many constraints, and it could be say 5 constraints, but it's paired with one input. So you need to select only one of them to control. And there can also be unconstrained degrees of freedom. And then you need to look at what we call the reduced gradients. So this is also an alternative. It's a bit less general than the previous one, because you need to be changing this. You need to be keep tracking of the constraint regions to be able to do this gradient thing here, finding the null space of these active constraints. But the advantage with this approach is that it's the selector is on the inputs, on the primal variables, and so it's going to be much possible to have much tighter control of the constraints, which is good for the economics. And actually, this structure is similar to the selectors used in advanced process control. So if you look at how selectors are used in traditional advanced process control, it's something like this. We have a selector here. We have one input, and I have, in this case, 2 outputs I want to control. So this block can be a max or min. So these are just some flow sheet or some block diagram symbols typically used, called max or high select, or this symbol greater for max, and minimum can be less than symbol or a low select. So you will find these are very common in industrial control systems, these kind of selectors. Sometimes I call it override, but I don't really like this word, because it's not necessarily an override. It could be just the optimal thing to do. And selectors, so I use for output or CV switching. So just a typical example, you want to keep Y1 at the set point. So, but this set point can be given up. So if this variable reaches its constraint, this selector will say, means that this input U2 will be selected, and it will no longer be controlling Y1. And you can have many constraints being connected to the same selector. And so you can see that there's one controller for each thing being controlled, and then you select on the inputs. So selectors work well, but they require pairing each constraint with a given input, which is not always possible. But a bit about designing of selectors. When we looked into this, I found out I couldn't find any design rules for selectors. So we actually wrote a paper very recently on this with Dinesh. So the first rule is to decide you're going to use a max or min selector. And the rule is that you use a max selector for constraints that are satisfied with a large input, and you use a min selector for constraints that are satisfied with a small input. Then there's the case, in some cases you need both a max and a min selector. And then there's the potential that there could be infeasibility because of the constraints not being possible to satisfy both at the same time. So then you have to give up something, one of the constraints. And then the rule is that you should put the highest priority constraint at the end. So I'll show you an example of how this works. So here is a typical problem. We want to constraint problem. We have a valve here, and we have some pressures and some equipment. We want to maximize this flow, but it also has a maximum limit. And there's limitations on the max and min pressure here, and there's a maximum opening for the valve here. So how can I make a control system to maximize the flow here? So it will be, this problem will always be at active constraints, and it turns out you can do it this way. You need two selectors because you have both a max and min constraint on the pressure, so obviously you need two selectors. Then there's also this flow constraint, and that is going to go into the min selector. And but you have two alternatives. You can have the min selector first and then the max, or you can have it the other way. So as long as there's no everything is feasible, there's no difference between the two. But if there's infeasibility, then it will always put priority on the last one. So in this one, we have the low constraint on the pressure on this one into the last block, and in this one we have the max constraint on flow into the last block. So that will be the difference here. This one will always satisfy this constraint, and this will always satisfy the Fmax constraint. So here I show you some disturbances on P0 and P2 I'm simulating. I will simulate these two structures. So here showing the responses. You see they are identical, except for this case here, where it's not possible to satisfy both of them at the same time. So, but for this structure, it will always satisfy the constraint on the pressure, but it will violate the constraint on F. And this one, it will always satisfy the constraint on flow because it's into the last block, but it violates the constraint on the pressure. So this is a simple way of designing a control system that makes you do exactly what you want in a very simple manner. And this example is always on constraints. So here's on the max flow constraint, and this region is on the pressure constraint, the P1 max, and the last period is on the fully open valve constraint. So this is always at constraints. So you don't actually need to solve an optimization problem to make this optimal. You just need to implement this simple selector structure. And I showed you that this can also be designed in a systematic way, as I just showed with the last two rules. Now let me give you another example, which I think is quite interesting. This is very common in chemical plants, that you have a series of units, and you need to keep production flowing through the system. And you need this is called the inventory control. You need so in this case, you have the feed rate given, and then you need to have the inventory control in direction of flow. So when you have more feed, this level goes up, and then this flow will increase, and so on. Now, some cases you can put the throughput manipulator where you decide the feed in the middle of the process, and then you need to have what we call a radiating control structure. So the loops are in the direction of flow in this way, and this loop needs to be arranged the other way. And you can have the case where you have the fixed product flow, and then all the loops are rearranged in this direction, in the reverse flow. So this is something you would like to look like, and you can see that as you move around the TPM, which could happen because of disturbances, you need to change the whole control structure. And also note one thing, I put low levels here and high levels there, and that's because this is actually beneficial, because when this flow rate is given, and if you then some temporary disturbance happens, say on this flow, this goes down, then I can keep production going by filling up these levels. And the opposite here, if you want to keep this production going and you have some temporary reduction in this flow, then you can just empty these tanks or keep emptying these tanks and can keep production going. So this is you would like to make something logic that makes you always have this situation. And it turns out you can do that by using selectors. This is a very smart selector strategy that gives you exactly all the structures on the previous slide by using selectors, bidirectional inventory control. It reconfigures automatically and with optimal buffer management. So for each part of the process or inventory, you have a high set point and low set point. So the high set point goes to the flow before, and the low set point goes to the flow after the inventory. And then you need the minimum selector to decide which one to use. And this also follows the rules that I was presenting before, and I'll show you how it works. So this is a case where we're starting from a case where we are producing a given amount. So this is we want to have a given flow rate of 1. So then this is given, and the inventory control loops will be going in this direction, keeping all the flows at 1 in this case. Now imagine there is a temporary disturbance in this location. So for some reason this drops to 0.5. Maybe there's something happening here, something been taken out of service or something. But we would like to keep production going. And I'll show you now, this selector structure will do this for you automatically. So when this goes to 0.5, we'll break. This loop is no longer being controlled, or this level is not being controlled. It will start dropping because this is low. It will eventually drop to the low level. When it drops to the low level, then this loop will take over, and this will now be not controlled anymore. And this will start dropping. And eventually, then this will drop to the low. And you see now that you are able to keep, only after some time, you really need to start reducing this one. You can keep this flow going for quite some time, as you can see in the simulation. This is shows the levels here. This is the valves openings, and this is the flow rates. So you can see that you can keep this green, this purple flow here going for a long time. Eventually, it needs to be reduced. And then at this point, this disturbance goes away, and it will rearrange itself back to the original structure, and it will refill all the levels by opening the valves, and it will go back to the original again. So it's almost like magic, you know, and it's a very simple control structure. And you can say, well, maybe you can use MPC here. Well, I think I would like to challenge you to design an MPC that does this. I think it's not easy because we have been trying. I think this is it certainly will be much more complicated, and it's even not clear that you can do it in a simple way. But this simple selector structure, which actually is just tracking the active constraints, is able to do it. So an important insight here is that for many problems, that the optimal steady state solution is always at constraint. And in this case, an optimization layer may not be needed if you, just by measurements, as we did in the previous example, can identify the constraints and then switch using selectors. Let me just mention, of course, that for all the controllers that I was showing you here, we will need to have some anti-wind-up scheme implemented, as we has integral action in the controllers. So usually I recommend using this back calculation scheme, where typically this tracking constant just select equal to 1, but the tracking time is the same as the integral time. So this is what was shown in the simulations. Okay, so what about this challenges for selector design? Well, it's first thing, it's not so obvious how to design these selectors, although I think with some insight or some rules you can help you. But there's some problems, and that's also that it requires you to be able to pair each potential constraint with one input, and this might not be always possible to make it, because you might be regions where this will not work. Another thing is that, of course, the stability analysis of switch systems is still an open problem. You can have high frequency switching occurring. You can have different problems, even chaos. So maybe one reason why people in theory has been staying away from these problems. They're not easy to solve mathematically and analyze. So that's selector design. Let me go a bit back to this list again. So far, I've only talked about the last of these simple elements, and still 6 more left here. I'd like to go just quickly through them very briefly. And then, well, you can ask some more at the end if you want some more about them. Let's start with the cascade control, which is something everyone knows about. So basically, cascade control is used typically when there's a delay on the measurement of the main CV. And to improve control, we introduce another measurement. And using this secondary measurement, we can then eliminate disturbances inside this loop, and we can eliminate also nonlinearity in this element. So that's 2 reasons for using cascade control. So a related approach, of course, that's used in optimal control is full state feedback, when you also use additional measurements, but this is an alternative approach, you can say. Then regarding this feed-forward decoupling linearization. In many cases in process industry, these are done using just static calculations. And I will just want to show you that you can use what I call transformed inputs for this as a unifying approach. This is also a bit related to something Shinsky talks about. There's no need to be limited to single measurable or manipulative variables, he says. If a more meaningful variable happens to be a mathematical combination of 2 or more measurable or manipulable variables, there's no reason why it cannot be used. So that's something that's used quite a lot in industry. But again, the problem with using it in industry is that there's no really methods for how to make use of it. But let me give you a motivation on ratio control. So ratio control is very common in process industry. It's used always when you mix flows. So here we're mixing like a concentrate Coca-Cola and with water, and want to make some lemonade here, for example. So we will typically here use ratio control, where this is the input, the MV, and this is the disturbance flow. Now, this ratio needs then generally to be the set point needs to be set by some autocontroller, which takes into account other disturbances and uncertainty. So this is a very common way of doing it. Now, here we use the transformed input, you can say, is the ratio between these 2 flows. But keeping this ratio constant does not handle disturbance in C1 and C2. Also, there might be nonlinearity in the loop that controls this ratio. So is there another approach that we could use instead? Yes, we can use this ideal of transformed inputs. So we can make some nonlinear function block. The V is some transformed input variable, which will be set by the autocontroller. The autocontroller is there just to correct for uncertainty and model mismatch and unmeasured disturbances. So how can we design this V variable? Well, it's very simple. You can you write down the equation, the steady state model for the thing you want to control. This is just, in this case, a static mass balance. And then you define the trans input just as the right-hand side of this equation. And then you get the transform system is just y equal to going to be c equal to v, y equal to v. So to implement this, you need to solve this equation with respect to the 2 inputs, so that this nonlinear function block will be the solution of this equation with respect to Q2. So it'll be this expression. And this gives you a perfect feed-forward control for disturbances in Q1, so C1 and C2, and also gives a linear response for the controller, autocontroller. So it's almost like some magic here. And actually, this is very closely related, if you look at the dynamic case, to the feedback linearization idea of Isidori and so on. So if you have a nonlinear dynamic system shown here, then you can introduce the transformed input again as being the right-hand side, but minus a times y when a is the tuning parameter. Now, Isidore usually chooses A equal to 0, but that's not a good choice because that gives you an integrating transform system. But with the A parameter, this becomes just a first order transformed system, which is linear, decoupled, and it's also, if A is diagonal, and it's also independent of disturbances. So it's again almost like magic. And to implement this, you just need to solve this equation here with respect to the physical input U. So that's can be solved numerically or analytically. And the value of V, which is the transformed input, is set by the outer controller, which could be a PI controller. So ideally, we don't need to change this V variable, but generally we need this outer controller to correct for uncertainty. And this has some limitation, this approach, of course, but it can be applied to actually many real processes. Just to give you a simple example, just look at the mixing of hot and cold water. So it's like, again, a mixing process. Two MVs here, both the two flows in, hot and cold water. And I want to control the total flow, and I want to control the temperature. So I write down the mass balance, which in this case is assumed to be just static. And so the first transformed variable is just the right-hand side, so it's going to be Q1 plus Q2. Transformed input, and the second transformed input is going to be the right-hand side of the energy balance equation, which is dynamic, minus this A times T, where A is a tuning parameter. And we're going to choose A, in this case, just equal to the nominal residence time, or the inverse of that. So we have two transformed inputs, V0 and V, and we can then, to implement this, we need to from a given value of V and V0, we need to find the U, and that's just done by solving these two equations with respect to Q1 and Q2. So that's this. And this, again, this works like magic. It makes a transform system that's linear, decoupled, and independent of disturbances. So this is a resulting transform system, as I said, linear, decoupled, independent of disturbances. And if you do some simulations here, just to show you that it works in practice, I'll show you some disturbance in T1, disturbance in T2, and set point change in the temperature, set point change in the flow. And you see that this is the flow following perfectly the set point. This is the temperature. It follows this set point by this first order response, and the speed there is given by this A parameter. And then you see there's no effect of disturbance here. That's taken care of by this transformation of this feed forward action. So it's almost like magic, but of course this depends that you have a perfect model. And you measure disturbances. But also in practice, when this is not the case, you can get large benefits of using something like this. So this is something we have been working on recently. Then to another case here we haven't considered yet. Number 5 and 6 on my list, that's when we have extra MVs. So there's two cases. Either use the extra MVs for steady state or just dynamically. So if you need extra MVs to handle all the conditions, then you can use something called split range control. It goes back a long time to like Ekman 1945. Alternative approaches use multiple controllers with different set points or valve position control. So I'll show you just how this works on a simple example. So assume you want to control the temperature in the house, and you have 4 sources of doing the control. You have 2 for use in the summer and 2 for the winter. So you have when it's very hot, you can use air condition. It's a bit not quite so hot, you can use cooling water. If it's getting a bit cold in the winter, you can use hot water, and it's getting really cold, you can use electric heater. But you don't want to use these at the same time, or you want to use one by one. And to implement this, you can make this split range block that shows you the order of how you want to use the blocks. And you can implement it very easily with just one controller that computes this internal variable V into this block, and this decides on how to use the different inputs. So you can get different gains there by adjusting the way you do this, the splits here. But you need to use the same integral time in all these loops, which can be a disadvantage here. So maybe a simpler choice in many cases is to use just alternative 2, which is multiple controllers with different set points. So here I have 4 controllers, 1 for each input, and they're working with different set points. So meaning that they will only be doing one, only one will be active at a time. So this also works really nice, and I think maybe it's often simpler than the other approach. Well, the set points have to be different, but you can always make, you could have made some auto cascade that puts them back to the desired set point. So this can be fixed up. A third approach could be what I call input resetting. That's when you always use the same input for controlling temperature. Like in this case, I'm just using the electric heat always for temperature. And the other controls are really just looking, resetting the input back again to some desired value for the heat in the case where, you know, when you are not really in the winter. So this is also an alternative scheme. And here I'm comparing the three. I would say that the traditional picktimes control is okay, fine when the MB ranges are fixed and it's easy to understand. This thing with different set points, I think, is often better, especially for cases where the ranges vary for the MBs. And the third case is generally gives you some economic loss, but it's nice if you always want the same MB to control the output. Yeah. Getting towards the end of my list here now, we also have this case where we have extra inputs that you need dynamically. And this will be the case of valve position control. So this is active all the time with the aim of resetting or mid-ranging the input. So just give you a simple example. Say you want to control this temperature in the heat exchanger. This is a hot steam outlet temperature using cooling water. So cooling water is your main input that's used for the steady state, but for dynamic purposes, you have added a bypass, which is not really optimal from economic point of view. So this bypass is used for the fast control because it has a direct effect, but you don't want to use it. So you want to set it back to a small value, like 5% only. And for this, you use this valve position controller or this input resetting controller that sets this back to 10% by manipulating the other input, which is the cooling water. So this is also a nice solution that can be used when you have extra inputs dynamically. Okay, so getting towards the end here. So what about MPC? Okay, of course, MPC has its merits, and there are cases where what I described to you just doesn't work or it gets too complicated, and MPC should be used. MPC also has large benefits for some very interactive processes where you can especially dynamically be much better. And if you know future disturbances and set point changes, then you can use the predictive capability of MPC to do much better. But in many cases, what you will see is that you can do equally well with this standard advanced control methods. And in some cases, you can solve problems which I don't even think you can do with MPC. So my conclusion is that a lot of these conventional advanced control methods, they work well in practice. Essentially, you're using optimization by feedback, by measuring active constraints and switching. You need to do the pairing of input and outputs because it's basically based on single loops. This can be nice because the engineer can specify directly the solution that you get, but the problem is that it might not always be possible for more complicated cases. So a nice thing is that you don't need the full model. You only need the model for the part of the system where you're doing the control. There's a challenge in terms of teaching and better design methods. And as I said already, MPC certainly may be the best solution for some problems, no doubt about that. But the main challenge, I think, is that you need a dynamic model for the whole process, and this is very expensive to get in many cases. And also that tuning may be difficult. And also it does not work on all problems, I think. So really the final solution, I'm showing this picture of academic process control community fish pond. So we have this big glory future here with optimal centralized solution, which I call the economic MPC in the beginning. Almost all the fish are going in this direction. There's one fish here going in this other direction here. Simple solutions that work. The old selectors and PID++. And there seems to be only one fish in this direction, and that seems to be me. So I'm hoping that maybe we can get some more fish to go with me here. I think this is an important problem to look at, and it has a lot of merits. And I think this could be a challenge for the control community. So thank you very much for listening to me.
Thank you very much, Professor Skogestad, for your stimulating presentation. And I would like to audience to go ahead with the questions. There are instructions in the chat saying that you have to formulate them in a written manner. But for the sake of time, I will admit questions of a live voice. You can raise your hand, and some of my guys will give you voice and video. Let's wait just a couple minutes, just while we get organized. Hector, please take a look.
Yes, first is Cristina Verde. She's raising her
Okay,
hand.
from plenaries to plenaries, here comes Dr. Cristina Verde. Go ahead, please.
If you open your microphone.
Okay, is now open. Professor Skogestad, thank you very much for the talk, for the nice presentation. And my question is about false and abnormal event in the process. How do you manage this in this advanced control when you have to optimize some things? Thank you very much.
So, but false, yeah, false. Well, in many cases, false, or it could be maybe some temporary restriction in the process can be detected by the measurements, the feedback, and then this can be taken care of automatically through the feedback. So in many cases, many faults can be handled the way I just showed by the selectors, especially. But of course, this is not if you talk safety system, that usually comes in addition to this. But I would say that these simple selectors can handle many faults. Yes, that's often the reason that they was put in.
Okay, thank you very much.
Okay, I have a question that is written, sorry, quickly by Alejandro Vargas. He did his job. And he asks, well, he makes a reflection. I guess using a multiple set points instead of a split range control makes sense if the controller is accurate in order to shoot down some controllers in some case. And then here come the questions. Am I right?
I think it's this solution I'm showing here with multiple controllers with different set points. For me, I haven't seen cases where it doesn't work. So it wasn't quite clear to me why you would think it wouldn't work. For me, it has the same application range as the split range control. The disadvantage of the split range control is that you need to specify all these these maximum values there. And if these change because of other things, then this doesn't work so well.
Thank you very much on behalf of Alejandro Vargas.
Okay, I have another question from Yadiel Martinez, doctor. He's asking, stability and performance are guaranteed by selectors?
No, I think not. This is one of the challenges I was mentioning. Selectors is a very difficult issue, and I think maybe this is one of the reasons why academic people haven't looked so much into them, because as I said before, it's really an unsolved problems when it comes to stability, especially as I said, you can have at least low, not global instability, but some local instability caused by different things. Delays combined with selectors is known to be a difficult thing to look at. So, of course, there are some cases where you can prove stability, I'm sure, but in general, there's no good theory for this, as far as I know.
Okay. There is another question from Ricardo Alvarez. Can you open your microphone and your video if you like, Ricardo?
Ricardo, you can formulate the questions directly. Open the microphone. Hector, if he has some technical problems, let's go to the next question.
No,
and then we go back.
He can open the microphone. Okay.
¿Puede o no?
Okay.
Sí. Vamos a otra.
No more questions here.
Yeah, I have a question.
Another question from Nishbalang.
Yeah, and what about the model? Because the problem in real application, I think the most important or the most challenged problem in real application are the models, the process model. So in order to design a simple controller in a real plant, in a real process, for example, in the case of the house, how we can construct the model that we will use to design the controller.
Yeah, now if you talk about, say, this solution here, which will be close to optimal economically, the models here you don't need is not a lot now if you use this solution, and that's the main advantage. Of course, you only need maybe a step response to tune each controller. So you need to be able to look at so you don't need the model for the whole system. You only need some local models for tuning controllers here. It's like you make a step in the air condition, and then you look at the temperature, and you can use this for tuning this controller and so on. So that's the main advantage of these traditional methods, is that they need much less modeling. They're more using like structural information that you have about the system, and you are of course making assumptions about how you link inputs and outputs together. But all of these things make it much simpler than to design the system afterwards, and it can still be optimal.
Okay. Okay, thanks.
How are we doing on time, Hector?
We are well because we have 5 minutes left.
Okay, I catch another question. Can I read it?
Yes.
This is from Pedro Lira. Professor Skogestad, is there a systematic procedure to conduct the input transformation, or is it case specific?
No, there's a systematic procedure. So for the static case, you write down the model and you take the right hand side, like here you write down the model and the selector transform the input being the right hand side of the equation. And the similar, if you have a dynamic equation, you write it down and take it as the right hand side minus AT. So this is a generic procedure. Now it doesn't work on all problems, especially if you have complicated models, high order systems, it might not be possible. Or then maybe you need to introduce measurements that are not really disturbances, but are outputs, and there's some problem with internal stability. This is a well-known problem from feedback linearization. We have the same issues. So this is actually quite close related to the theory of feedback linearization that people have been working on for 30 years, 40 years. This is just showing it in a bit different context than they do in feedback linearization. But when you look at it, it's really the same thing.
Thank you very much.
There is another question.
Thank you very much on behalf of Pedro Lira. Go ahead with the next question.
Yes, it's from Yadiel Martinez. Now, if you like to formulate a question, Yadiel, you can open your microphone. Or if you want, I can read the question.
If you want to question, put your microphone and go ahead.
Yes, I am René Galindo. My question is about the feedback linearization on the decoupling using feedback. If it is possible after that to recover the robustness due to if there is no perfect cancellation of the dynamics, if we can recover the robustness with the PD controllers, the linear controllers. This is my question.
Yeah, so you're talking about this feedback linearization case, yes, and when you have model error. Yes, this is an interesting question. Of course, the reason for having this autocontroller is to do what you say, is to counteract the effect of unmeasured or disturbances and also model error. So that's so it can recover, of course, to some degree. That's the whole idea here. So this is more like a conventional feedback control, that's looking at the output and just changing the input. But this input is not the physical input, that's the transformed input to the system. And then, so the system that this controller sees is much simplified. But so, so the question, I think the answer you can say is yes, it is possible to recover it using the conventional feedback control, essentially.
Okay, thank you.
I have a question from Dr. Jaime Moreno. If I can read it or he can set his microphone. Please choose.
Yes, hello. Good morning, Mexico. Good afternoon, in Norway. Thank you very much for the nice presentation. It is very stimulating, and going against the MPC flow, it is not very easy, but I think it's very exciting. You have many proposals that you have done, and it seems to me that for each of them, you need some kind of insight into the process. I mean, this is not, or doesn't appear to be a only systematic procedure, but how can you do that systematically? And for example, how can you teach this? How can you find a solution for a particular problem? Is there a systematic way to do that? Thank you.
Sorry. If it is teachable, go ahead.
It's a good question. I mean, this is something that I'm working on, doing exactly this, trying to make it more systematic. Now, one important thing is this thing about active constraints, because so if you can identify the active constraint to control it, then essentially by definition you are going to be optimal. But I agree with you, that this is not at a level where it's completely systematic, and maybe it will never be, because it's not really. It's like putting together different elements here. So that's always going to be the maybe disadvantage compared to like MPC, which is seemingly systematic, but I think it's not always in practice so systematic, because it can't easily cover all problems. So I think there's always going to be some element of insight and at least knowing some examples. But my aim is to minimize this as much as possible and make it more systematic. So I want to write a book on this someday when I put things together and make it into something that's going to be used by engineers and also people and for teaching.
Yes, thank you.
Thank you very much.
Okay,
I think that we are running very close to the end, no?
Yes, I think that the time is over. So if you
just let me share the screen to say goodbye.
Okay.
Thank you very much for listening.
And thank you very much, Professor Skogestad. And this is to show the audience that also Norwegians can sing Mexican songs from time to time. That was in Cancun in the DICOPS meeting. Thank you very much, Professor Skogestad. It was an honor to have you talking with our people.
Thank you very much, Professor Skogestad. And thank you all of you for being here.